Hello, everyone. First of all, I would like to thank you much for introduction. First of all, I would like to say thank you to organizers of Hypercomplex seminar for possibility for organizing this year online and also for possibility to give a talk. We always have very nice and very warm, memories about hypercomplex seminars organized by Professor Lebenovich in Bedlevo, where we had a nice cooperation, a nice scientific exchange, and also nice social time.
Could you switch to full screen mode because your presentation is only partly visible? Control L, I guess.
Yeah, I will try, but sometimes when I switch to full screen mode, it's not possible to. Okay, I will try.
Maybe in tools. In tools, you have option tools.
Yeah, I know, but sometimes it's not possible to switch between the pages.
No, there is full screen mode. Go down.
Yeah, I know.
All right. Well, doesn't work. Okay.
Okay, it looks okay. So today I would like to talk about asymptotically best possible vector inequalities for Fourier sums on classes of generalized Poisson integrals. The presented research is joint work with Professor Anatoly Serdyuk. If I go too fast or something, please feel free to interrupt me. Okay, so let's see L sub infinity and LP be standard spaces of two periodic functions with standard norms, which we will denote by norm with C, norm with infinity, and norm with sub P. Okay, and we will consider the classes C super alpha sub beta LP. For where alpha and R is positive, beta is some real number, and P runs from 1 to infinity. And these classes are the set of two periodic functions, which are represented as convolutions of the form. In this convolution, the function phi is some function from the space LP, and the P sub alpha R beta is a generalized Poisson kernel of the following form. So just sum from 1 to infinity, exponent, and by this cosinus. And these kernels of the form 2, when in the case when R equals 1 and beta equals 0, they are usual Poisson kernels of harmonic function. And when R equals 1 and beta equals 1, they will be Poisson conjugate Poisson kernels.
Excuse me, are you on your slide number 1? Because we only see your slide number 1 right now.
Oh, it's maybe because of the full screen mode. Wait, I just maybe leave that in a second.
Maybe you can close and reopen. Okay, now
it's open. It's often. Okay. Can you see now? Maybe I just.
Now it's slide number 3. Now it's slide number 3, right?
Yeah. Can you see now the whole slide?
Yes.
Okay. Because it's often happened with full screen mode. That's why I usually keep it like this. Okay, so maybe I will repeat the slide because it was not possible to see it. So we will consider the classes of C super alpha sub beta LP, which are representative of the convolutions of the forms 1. In this convolution, function phi belongs to space LP, and P sub alpha R beta is a generalized Poisson kernel. And this generalized Poisson kernel has the form 2. Alpha and R some positive numbers, beta is real number, and P runs from 1 to infinity. And these kernels, if R equals 1 and beta equals 0, the generalized Poisson kernels are just usual Poisson kernels, and when R equals 1 and beta equals 1, they conjugate Poisson kernels. And should we notice this function f and phi, which in the equality 1, function phi here is called the generalized derivative, and we will denote it with f super alpha r sub beta, and also we consider the subset of functions f from the classes C super alpha r beta LP, namely the subset when the function phi belongs not only to LP but also to the unit ball of space LP. And we denote these classes by C super alpha A sub beta P. And also it should be noticed that all these classes of generalized Poisson integrals, they are for all positive R, they are classes of infinitely differentiable to pi periodic functions. And namely, when R equals 1, these classes are classes of functions which admit in regular extension into the strip of complex plane, namely they are classes of analytic functions. And for R larger than 1, these classes are actually the classes of entire functions. We will denote by tau sub to n minus 1 the space of trigonometric polynomials of degree at most n minus 1, and n von f LP be the best approximation of the function f in the metric space LP. Namely, it denotes the following quantity. We take the infimum for all trigonometric polynomials of degree at most n minus 1 and approximate this function with the polynomial. And in the same way, it's here we take the norm in the space LP, and the same name we denote by NF in sub C, the best uniform approximation, where we consider the norm in space C. And then by rho sub n f von x, we denote the quantity of the form 3. So this is in this quantity the s sub n minus 1 the partial Fourier sums of order n minus 1 function f. So actually this is deviation of the function f from its partial Fourier sums of order n minus 1. Then it's possible to estimate the deviation of norms of this norms of rho in this metric space C with the help of the following equalities. So in the form 4, and equalities of the form 4 are called by Lebesgue inequalities. And in this inequalities, the quantities L sub n minus 1 are Lebesgue constants of Fourier sums, and they have the following form. Here, d sub n minus 1 is well-known Dirichlet kernel, and we can, of course, calculate this constant. And then Fourier showed that the asymptotic equality for Lebesgue constants Ln, which has the following form: 4 over pi squared log n and plus some over 1. But the results of Lebesgue were clarified in the next years. Namely, it was shown in 1986 that for this constant we can find the more exact estimate, namely the following estimate holds, and also where so we can find that for the norm of rho n in space C, we have the inequality 5. And for this reminder, where it was known the estimate is only O from 1, we can get some such estimate like 2.271. But the inequality obtained by Lebesgue is asymptotically exact on the whole space of continuous functions. But if we consider some subsets of this function, this inequality will not be exact anymore. It even will be not exact anymore by the order. For example, Skokov established the following quantities for the deviations of rho n and C. And he also proved that this inequality is exact by the order on some specific classes C von epsilon, to which are defined in the following way. So our purpose was to establish Lebesgue inequalities for the function from the classes C super alpha A sub beta LP which are subclasses of continuous function, and namely infinitely differentiable functions. And about these classes, for the Lebesgue equalities were established in the case when R is larger equals 1 and for all P from 1 to infinity. But for the case when R from 0 to 1, they were known only for case when P equals infinity. Namely, P equals infinity, it's namely we can consider like in a norm in space C. So it just has estimate 6. Also, it should be noticed that when we'll consider the least upper bound of our quantities rho n in C, and we'll take this over the classes C super alpha sub beta P, then we obtain the following quantity, and this, which we denote by calligraphic epsilon, and from the classes C super alpha sub beta P in C, and this quantity is to call the approximation by Fourier sums in sums for the classes from space of generalized Poisson integrals in the uniform metric. And before going to Lebesgue inequalities, I would like to say some history about the quantity of approximation by Fourier sums of class of generalized Poisson integrals. For this classes, for the case when R equals 1, the results for R equals 1 and P equals infinity, asymptotic qualities were established by Nikolsky, which have the following form. I will take the brief excursion, brief history overview about results. Here, K is complete elliptic integral, and then this equality was clarified by Stechkin, who established the following asymptotic formula, which more clarified the result by Nikolsky. Then for all parameter P from 1 to infinity, the result was generalized by Serdyuk in 2005, and it has the following form. And it also should be noted here the K is the complete integral, but the asymptotic quality could be written in terms of Gauss hypergeometric function, because the complete integral is related with the help because of the reason of the equation 16. Also, we could have some particular cases for P equals 2, namely to have not even asymptotic qualities, but to have even equalities. And now I will tell about the case R equals 1. For case R equals 1 and P equals infinity, asymptotic equalities for the quantity approximation by Fourier sums were obtained by Stepanyuk, who showed that asymptotic quality of the form 19 is true, where for the remainder term gamma sub n, the following estimate holds. Then this equality, asymptotic equality was clarified by Telekovsky, who showed that the estimate 20 takes place. And also for R equals 1 and for all for R larger than 1 and for all parameters P from 1 to infinity, the asymptotic qualities were obtained by Serdyuk in 2005, and they have the form of 21. And now the most interesting for us case when R is from larger than 0 and smaller than 1. Here, the asymptotic qualities were known only for case when P equals infinity. It was done by the work of Stepanyuk, who showed that asymptotic equality 22 is true. And about other only for P equals 2, but for all other values of P, the asymptotic qualities were not known. By f from A, B, C, D, we denote the Gauss hypergeometric function on the form 23. And also we will denote by n0 the smallest number such that the following inequality is true. And we always can find such integer n, or smallest integer n, because if n goes to infinity, the first term goes to 0 and the second term goes to 0. So it means that from starting from some number, they will be less than some 1 over 14, or this number for p. We will use this n0 for formulation our theorems. Theorem 1. If r from 0 to larger than from 0 to 1 and p from 1 larger or equals 1 and less than infinity, then for all p from larger than 1 and less than infinity and n which is larger than n sub 0, the estimate 25 is true. And here in this estimate is a bit more than asymptotic equality because we also give the estimate of the remainder in terms of parameter alpha, beta, and r. And when p equals infinity and n is larger or equals n0, then the estimate 26 is true. And for these quantities, gamma sub n p2, they are bounded above by the number 14 pi squared. Then also for case when p equals infinity, we got the estimate 27, which clarifies the results by Stepanyuk obtained previously. And it also gives the estimate of the remainder for the constant interminder. And now the following table contains the exact values of, if we represent the quantity of approximation of Fourier sums of classes from generalized Poisson integrals in the form exponent to the power minus alpha n to the power r, then for this main term, a sub n, we can show the following table. So for all cases when r equals 1 and or r larger or r larger than 1, they were known, and now we also finished the cases for r from 0 to 1, and we can say that the problem for establishing asymptotic equalities for approximation by Fourier sums is solved completely. And now going to our Lebesgue inequalities, we showed that theorem 3 it gives an estimate if r is larger than 0 and less than 1, alpha and beta, alpha is positive, beta is real, then for p larger than 1 and less than infinity, for any function f from the class c super alpha r sub beta lp, and for n larger than n0, the following inequality holds. Here f is our Gauss hypergeometric function, and S sub n is best approximation of generalized derivative. And moreover, we also showed that this equality is exact because it's always possible to find a function f such that the inequality 28 becomes equality. So the equality for this function f calligraphic, the equality 29 will be true. And also in this, in 28 and 29, for the quantity gamma, is bounded above by the number 14 pi squared. And another theorem is for case when p equals 1. also if r larger than 0 and less than 1, then for a deviation, our deviation is the following inequality setting. And this inequality is we also show this inequality asymptotically best possible, because it's always possible to find a function calligraphic f from the set C super alpha beta L1 such that that the inequality setting becomes the equality. Namely, the equality set 1 will be true. And also for this gamma in the estimate, so here we have the main term, and gamma is some constant which multiplies with remainder. For this gamma is such that it's bounded by above by the constant 14 pi squared. And also I would like to say a few words was the case from for when R belongs from 0 to 1 is most interesting, because we also got not only the Lebesgue inequalities and asymptotic qualities by Fourier sums, but we also got the estimates for some norms of the geometric series, which could be interesting for other problems, which were not so for actually asymptotic qualities for norms of reminders trigonometric series in the space LP, which could be interesting in some factorization. And the references which was used in the talk. And thank you very much for your attention.
Thank you very much for your presentation. So are there any questions? Please give some questions. So maybe I will have one question. So can you make an explicit example of application in physics or in electrical engineering with your results? Do you see any direct application?
I cannot say very direct application, but it is, I say what is important here, that for example, in Lebesgue inequalities or in approximation by Fourier sums, we got not only just asymptotic inequalities, because when we get asymptotic inequalities, we have here instead of, in reminder, just Landau symbols, right? But here we can, when we for each concrete n, we can find the explicit estimate, and it's could find some application for when you need to have some numerical experience, for example. That you can for each n you can find some real estimates, not only with Landau symbols.